Oh, sorry about that. Uh, I had to finish cutting that last piece of wood there. Um, so, what are we at here? What are we? I guess we're continuing our discussion on the fundamental theorem. You guys had some homework problems, homework helper 8.1. And what about this multiplicity thing? Do you remember that word multiplicity? It's something that we didn't bring up yesterday, but I'd like to talk about it now. Looks like it's the number of times that a root is counted. So every root has a multiplicity, but some multiplicities are maybe a little more interesting than others. Like honestly, number 1, did you write x equals -5 twice? Well, you should, because we need to have 2 solutions, right? It's a degree 2. Well, that means that -5 has a multiplicity of 2. Again, because it's simply counted twice. Look at problem 6. Looks like we got some interesting answers there. We have 0 twice. Well, that means 0's got a multiplicity of 2. But the other answers, they also have multiplicities. It's just that they're there one time. So 5 and -4, they both have a multiplicity of 1. A little more on that in just a moment when we get in today's lesson. I just wanted to follow up on just perhaps 1 or 2 more problems. Did you get number 8 right? And what about number 10? Just kind of working a little bit with I. Remember, I squared equals -1, but then we can kind of proceed to make some other conclusions, like I to the 4th equaling 1, I to the 3rd equaling -I. And yeah, it looks like if you kind of simplify that a little bit, you're basically going to get all of your values to cancel out to equal 0. So in fact, it is a solution when you plug it in. So what's next as we kind of lay the groundwork here, the fundamental theorem? So I thought what we would do is focus on the graphs today and kind of remember some things about behavior. Remember, these polynomial graphs do have behaviors, but of course we're talking about their polynomial behaviors. So if I was asked to graph this particular function, it would still be super important to figure out the roots, because remember, the roots are going to be the same as the x-intercepts. But I'd want to even just kind of note right now that this root of 2 has a multiplicity of 2. That is because it gets counted twice. It looks like I also get a root of -4. And remember, both of these roots are going to be x-intercepts. So, of course, that'd be a great place to start on this graph. What else do you remember about the behavior of a polynomial graph? Did you see this leading coefficient? Remember, if the leading coefficient is negative, your graph is going to be going down to the right. So you can kind of force the graph to do that. And I think if you kind of like multiply this polynomial out, I'm not going to actually multiply it out, but if you kind of think about multiplying it out, eventually you would get to the x to the 3rd power. You would basically get a degree 3. Remember, that's an odd degree, and odd means opposite. That is opposite end behavior. So if my graph's going down to the right, the opposite would be that it has to go up to the left. Now there's one more thing, and it has to do with that multiplicity idea. Remember, if you have a multiplicity that is even, that is, if the multiplicity is counted twice in this case, we're going to also have an interesting behavior on the x-axis. What is that, you say? That's right. It's going to just touch the x-axis. It's going to kind of bounce off the x-axis. I'm talking about the graph as it just touches x equals 2, but then, of course, passes through -4. And if you connect the dots, you end up with your polynomial graph. So what did you remember there? What is it that maybe you need to hear again? Let's try it on another problem. All right, so how are we going to graph this polynomial? P of x equals x to the 5th minus 16 to the x. Well, you can go through the same kind of analysis. You can look at the leading coefficient. It's pretty clear that it's positive. Oh yeah, remember, if you have a positive leading coefficient, that means that your graph is going to be going up to the right. We also have the degree. It's a degree 5. Remember, that's an odd degree, and odd means opposite. We're talking about the left side, of course, being the opposite of what happened on the right. So looks like it's going to go down. What else do I need here? That's right, I need some roots, right? Now, if I need some roots, I need to solve this. I'm pretty sure that the only way to solve this is to get to the business of some factoring. So let's take out an x. That'll get this thing down to x to the fourth minus 16. Be careful. You actually can keep factoring x to the fourth minus 16. You realize that, right? That's a difference of squares. It's just kind of a bit of a higher power. That is, the x to the fourth is going to be split into x squared. Then I can go to the business of the plus 4 minus 4. So we kind of have a little bit of a unique difference of squares, but nonetheless, I can factor it a little more. I think I'm at the point that I can deduce that I've got a root of 0. I hope that you would deduce that this is going to include a plus or minus 2. What about the roots of this one? Imaginary, right? Yeah, imaginary. So plus or minus 2i, they're not going to show up on the graph. Okay, but I do have some roots here. And the truth is all those have a multiplicity of 1. So if I have a multiplicity of 1, when I get to the business of putting them on the graph, it just means that the polynomial is going to pass right through those roots. It's going to cross the x-axis. So we draw a graph that's going to cross the x-axis, turn, and connect the dots in this manner. Are we ready for some conclusions? Okay, so remember, if you have odd multiplicity, okay, and again, multiplicity is simply the number of times that a root is counted. If you have odd multiplicity, you're going to cross the x-axis. It's going to be kind of like a normal behavior, you might say. But the even multiplicity, that is, if a root is counted 2 times, or maybe it's counted 4 times. So we're talking about the root here. If you have an even multiplicity, then you're going to be tangent to the x-axis. Now, tangent is just kind of a fancy word for touch the x-axis. You know, like sort of just bounce off. But we also have this end behavior thing going on. End behavior, we're talking about what happens on the far left and on the far right. And perhaps you did a little bit of like an end behavior dance last year. Okay, not too much dancing here, but still the same rules. That is that you're going to have opposite end behavior if it's an odd degree. Odd means opposite. And if it's an even degree, then we're going to have the same end behavior. Now remember, degree, we're talking about the highest exponent. But there's kind of one more piece to this, right? Perhaps it's maybe the first thing that you actually think about. It's the leading coefficient. And if the leading coefficient is positive, it's going to tell you that the graph goes up to the right. But if the leading coefficient is negative, it's going to go down to the right. Just a couple more examples. When you're ready, we're going to flip to this next problem here. Our goal is to still basically graph this, kind of understand the behaviors. So I got x, the quantity x minus a squared. A, x minus a. Well, yeah, let's say that a is assumed to be a positive number. Okay, so again, x minus a would seem to suggest that then x equals a, which again, we're going to assume is a positive number, would be a root. Of course, x equals 0 would be a root. Don't forget about that. And I think we can graph this. We know where 0 is. And if a is just going to be some positive number, just put it somewhere that's positive. We have a leading coefficient that's positive. Okay. Remember, the degree is the highest exponent when you expand the problem. So this is of a degree 3. That's another one of those odd degrees. There's just one more thing going on here. It's our multiplicity. Yeah, technically, x equals a is actually counted twice. So if x equals a is counted twice, we have to get ready to just be tangent at x equals a. So the graph goes up to the right. I'm going to be tangent. That is, I'm going to kind of bounce off. I'm going to pass on through at x equals 0. Opposite end behavior. We got our nice little graph going down on the other side. All right, I think we can do these. Okay, and this is always a good problem for a student to try on their own. You know, you can always pause the video if you want to do that. It's going to be our last example, so you can make sure that you're getting the idea of how to graph one of these polynomials. Once again, a and b, it would be assumed that they're positive numbers. So you mark them accordingly, assuming, again, that a and b are positive. All right. I assume if you are watching, you're ready to see the answer. I hope you thought about it a little bit. Let's get to the business. The root, 0. But remember, that's going to have a multiplicity of 2. Okay, so we'll keep that in mind, a little bit of tangent. How about negative a? Now, if you're like, I thought you said it was positive. Well, negative a would be the root. Okay, so I'll have to obviously put that on the left side. And then, of course, b. Now, make sure you notice that both a and b have an odd multiplicity. That just means that they're going to have that regular behavior. They're going to cross the x-axis. Before I graph this, I need to think about my leading coefficient, but I also need to think about my degree. And the degree is just kind of like counting up all your x's. I got 2 of them here, another one here, so we're up to 3. And then I'm going to end up with 3 of them here. Even though I'm not expanding the problem, I still know that I'm going to get 3. Looks like I got a total of 6, a degree 6. Now remember, if you have a degree that's even, then your graph should be the same on both sides. Let's see if it's going to work. Graph goes up to the right. It's going to cross through A. Oh yeah, it's going to have to touch at 0, and it's going to cross on through at negative A, and I'll be dang, it's going to be the same on the other side. Okay, so the problems always work, right? If you're using the rules correctly, you're not going to end up with like a missing part of your graph, or the dots don't connect. So it looks like, once again, we have the correct behavior. Now, you should be ready to do the take-home mini check, and I'm going to get back to my shop here. I think I got a couple more pieces of wood. Don't forget the safety goggles. Multiplicity of 2.